Hi everyone, and welcome to this online training session. My name is Simon Grandin, and I'm the photogrammetric workflow specialist here at SimActive. Today, the topic of my online training session will be how to effectively combine LiDAR data with imagery. The availabilities of LiDAR and photogrammetric data is getting much more popular. Um, and so today we've decided to do an online training session to how to effectively combine those two types of data. Um, so today, what you will learn is basically I will start with a much more knowledge part. So we'll talk about understanding the difference between LiDAR and photogrammetry. And after that, we'll go a bit more technical into Correlator 3D. And I will show you how to import LiDAR point cloud in Correlator 3D, registering LiDAR data and images, orthorectifying on LiDAR DEMs, colorizing LiDAR point cloud, and then I will show you also a few practical elements such as change detection tools and contours generation on your DEM. So let's start by understanding the difference between the LiDAR and photogrammetry. So what is LiDAR and what information does it provide? Well, LiDAR stands for light detection and ranging, and it comes in different types of LiDAR sensor, such as discrete return, full waveform LiDAR, multispectral LiDAR. Today, for this webinar, I'll mostly focus on discrete return LiDAR, since it's the most popular sensor on the market, and I think it's the most available sources of LiDAR data in the market. LiDAR is a remote sensing technology that uses the near-infrared lights to send pulse and measure distances. Um, in order to have accurate data with LiDAR, you also need a highly precise GPS that will give you a position of the instrument in an XYZ position, but also a precise IMU that will give you the roll pitch and heading direction of the airplane when the acquisition is done. Uh, LiDAR data provide in a 3D coordinates, such as the X, Y, and Z measurement, but also provide an intensity measurement with the amount of intensity that is returned from the pulse to the instrument. And now, how does LiDAR differs from photogrammetry? Well, I'll show you a bit the advantage and the disadvantage of each other. First of all, the LiDAR has a few advantage, such as the quick collection. It's quite easy. It's much more faster to fly LiDAR, since the overlap between your strips are way less than what is required for photogrammetric. Usually for LiDAR, you could have probably between 20 and 30% of side overlap between your strip. It's also well suited if you want to have a highly accurate digital terrain mapping, because it can map above the vegetation, and therefore for some specific applications such as forestry, or if you want to map previous glaciation and the terrain, well, LiDAR could be well suited for those kind of elements. Also, another advantage with LiDAR is it could be flown days and night, since it's an active remote sensing technique. It doesn't need an exterior source of lights to be used. Well, it sends its own energies and then collect it back from the sources. And also, there's no geometry distortion, or less than what we have with photogrammetry, and so that's another advantage. However, there's a few disadvantage compared to the photogrammetry. Well, the first one is probably the cost. The cost of such LiDAR elements are really high compared to the UAV. Photogrammetric data is much more accessible to everyone, which of the cost of the software are less expensive. Also, you could do processing, photogrammetry processing, which really um, low end UAV, such as and it's available for everyone. Another disadvantages is sometimes if you want to bring the intensity in your analysis, well, there's a phenomenon of striping for the intensity because the intensity really varies in with the range and also the elements that the pulse is getting hit to. So when you look at your intensity images, you could also find some striping images from flight line to the other flight line. However, it seems that some technique are trying to get this problem solved in order to have a to normalize the intensity over different flight line. And I think the last disadvantages of LiDAR would probably be the classification of your point cloud. It usually requires high-end software that are quite expensive, and it's also it could be also a lot of labor time um, expected. Since if you want to classify your point cloud as ground or non-ground, or also vegetation or non-vegetation, depending on how far you want to go with your analysis. As for photogrammetry, well, the advantages, I think the first one is it brings out the color to the point cloud, which is a big plus compared to LiDAR that doesn't really have this color. The color brings a much more, it's as I said, it's much more human friendly because it's easier to analyze since you have the RGB information. As I was mentioning also before, the cost of photogrammetry is much more accessible for um, for everyone. It could be much more cheaper to have a small UAV and do some small photogrammetric project, and it's more affordable for a wide range of user. The main disadvantages is well, on certain areas, well, you cannot map under elements such as trees. So if you want to measure the height of your canopy in dense forest, well, photogrammetry is not well suited because you will basically have the top of your canopy. Well, you maybe need to have lidar to have the under your canopy. The post processing could be quite long if you have big data a big amount of data to process. Um, well, once you have all your images, well, you need to do your aerial triangulation, tie all your images together, have a nice bundle block adjustment. Then uh, you need to perform dense image matching, which could be hardware consuming. It sometimes require good hardware to process such big projects. And also, it's weather sensitive. The photogrammetry is really reliable on the type of illumination that you have, or on the type of weather you have when you're collecting your data. You don't really want to have too much shadows in your scene because shadows will affect the texture of your imagery. So the content of your imagery is really important when you're trying to do some dense image matching, because low texture will give you some depth perspective problems when matching two images together. And also, well, one big disadvantages of photogrammetry is it affected by occlusion. In order to generate an accurate 3D measurement, you minimum need 2 points of view. You minimum to see the point from two different perspectives. So the occlusion could be a big factor, especially if you don't have the appropriate overlap. Well, the occlusion could be much more important. Uh, However, having said that, I think the best way to see those type of data is you should not see those as two competitive source of data. I really suggest that you see them as a complementive source of data. when they're all used together, I think it's the best way to get most of out of your data, to take the advantage of each of them and then merge them together. So today, I think the topic of my presentation will really show you how to have the best workflow possible to implement those two type of data together. So um, so now, with our latest version, Correlator 3D 8.3.5, we now allows the importation of a LiDAR point cloud to be transformed into elevation data, such as surface model. It's something new that we did on our last version because we had the demand of bringing LiDAR data in order to stitch it during the aerial triangulation and make sure that you have a LiDAR aerial triangulated model with your images. So basically, there's a few things to remember if you want to import LiDAR data in Correlator 3D. Well, the first thing is your point cloud need to be in the LAS format. So it's usually a standard format for LiDAR point cloud. And then in the software, you'll be able to import this point cloud. So let me show you how it works in the software. So as you may see here, you have the visual interface of Correlator 3D. A quick overview. Well, you have all the buttons are in a sequential order. So you have the open and new project, open or close a project. Then we have the automated workflow that for mostly beginner user, if you want to generate a one-click button solution for your photogrammetric process, which could be debated. And also you have all the information or all the other steps here in your bar. So the first one will be the AT, then will be the DSM extraction, the DTM extraction if you want to do some editing also, and then the Ortho Rectification, and finally the mosaicing modules, which will lead to the 3D generation module. So if you want to bring your LiDAR point cloud in Correlator 3D in order to create an elevation data with it, well, you could go into the File button, into the Import, then DEM, Import the last file. So you'll be able to select your last file, which in this case I've brought a strip of LiDAR, and then from there you'll be able to generate a surface model out of this LiDAR strip. So basically here I have my LiDAR strip, and the goal is to create a digital surface model with it. So if I bring more than one LAS, well, at the end, all my LAS file will be transformed into a raster way, and then all my rasters will be merged together in order to have a digital surface model, a LiDAR digital surface model, as we have here. So just to show you a bit the process that's happening behind this transformation from a point cloud to the raster form. Well, we do take the density point into account and try to find the optimal resolution of a cells regarding the density of your points. Once it's there, we interpolate all the points that are belonging to the cells, and then we'll be able. So if there's more than one point that fits in one raster cells, well, we'll try to interpolate them in order to have a surface model that will be used for your photogrammetric processing. Another thing that's important is if you want to ortho-rectify your image on your DSM LiDAR, well, I personally think that LiDAR is much more or it's better suited for true ortho, since we have a sharper edge on buildings, and it gives usually much more greater results if your aerial triangulation is well done on your LiDAR according with your LiDAR system. So now, if you want to registering your LiDAR and your imagery together during your aerial triangulation, I will suggest you probably two type of workflow. One is more conventional, which will be to control your LiDAR so it will be to take some GCPs on your LiDAR and then integrate it in your images system. The other one would be based on the intensity of the LiDAR. So I'll show you both workflow, how to use them. So as I said, the first one will be using the intensity and the surface model to co-registrate your imagery and your LiDAR together. So the main goal here is to use the intensity as the planimetric accuracy and the elevation data as the vertical accuracy. So depending on the quality of the intensity that you have, you may be able to bring during your project creation your intensity, and we'll try to do a feature matching when we extract the type points with the intensity. So we'll try to find common elements from the intensity layer through the images and try to find common type points to register both sources together. So the first step will try to be it will try to be an automatic way. However, sometimes if there's too much a difference between the intensity and the image texture, well, you may have to add a few links between your intensity and your imagery. This workflow also apply for people that are flying UAV mission over and over again, and they want to use previous mission results as ground reference for the next for their next project. So you make sure that your project are stitched on your previous project, so all your sources are have a good absolute accuracy over all your project together. The other method, which is probably a much more conventional method, would be to add some ground control points from your LiDAR through your AT. So it's the same principle a bit if you're using target on the ground with your photogrammetric processing, but instead of using ground control points from the ground, well, those points will be extracted from the LiDAR, and you'll be able to try to match them together. What is the expected accuracy out of this? Well, the overall accuracy really depends on your LiDAR accuracy. So if you have a really good as LiDAR is quite accurate, well, you should be able to bring down really closely the accuracy of your bundle adjustment on your LiDAR. So in the software, if I show you a bit both workflow, so the first one will be to integrate the intensity layer and the elevation data in order to try to do an automatic type point detection between both sources. So if you want to do so, you'll have to bring in the intensity layer as a reference ortho in your project tree. So you could add the little plus button here and then bring a folder where all your orthos, in this case will be the intensity, are saved. And the other element that you need is basically you will need to have a DEM loaded. So in this case where you're using your LiDAR as ground reference, well, I think you really want to have probably take some ground control points on bare earth data. So you want to make sure that on open area, well, your photos and your LiDAR are well matching together. So once when you have loaded those data, and then you run your type point extraction, the software will try to to find some common type points between, in this case here, the intensity layer, which is loaded right here, and then with your corresponding images. The number of type points that probably needs to be done between your intensity and your imagery should be roughly similar as if you were using GCPs. So you don't really need too much of common type points between both features. What's really important is you really need to be. I think you'll need to really make sure that the type points that the software found were corresponding between both sources. When you do the bundle adjustment, if you want to use an elevation data and an intensity features as a reference data, you'll go into your aerial triangulation module, and you'll be able to see the green dots of my images. And here is basically the intensity layer that serves as a reference ortho. Also, I see that some links are getting into this reference ortho, so I could imagine that those links were found between the intensity layer and those images. So as I said before, if you want to combine your LiDAR and your intensity, well, you'll do your bundle adjustment. So the window of the bundle adjustment is the same as if you were using some ground control points, but the main difference is instead of using the ground reference as GCPs, you will use the reference ortho and the current DEM that are currently loaded in your project. One element that's quite important is, let's say you have more than one elevation data that is loaded in your project tree. Well, the software will use the one that is checked in your project tree as the reference sources. So if you want to use your surface model as the reference sources, well, you need to make sure that the surface model is checked in your project tree. Same thing with the reference ortho. As for the other parameters, well, the parameters stay the same. So you'll have different. You will have also different parameters for the EO adjustments of your images. You could do a full AT on constraint, so the software will do an image adjustment, an individual image adjustment for each images without any uncertainty. You could do it with a constraint mode, so you'll be able to constrain and really keep the accuracy of your input EOs. You could also do a simple bore side calibration, so we'll try to calculate a mean shift between your LiDAR and your imagery. If the shift is constant, we'll try to move the block over your LiDAR imagery. And so on. Same thing with the sensor calibration. So the sensor calibration, if you have a metric camera where all your distortions are already measured in the laboratory, and you have a quite confident calibration report, well, you don't want to optimize, or you don't want to play with those values. If you want to constrain some of your parameters, because for some specific reason, you could constrain, or you could optimize only certain parameters, or you could most of the time for non-metric camera leave it at unconstrained. So the software will try to refine the camera distortion and really retrieve what's the interior geometry of your camera when those imagery were acquired. So the main thing here is when you will analyze your results, When you use the ground reference method, which is the reference ortho and the current DEM, if you take a look in your quality report, you will find all this information. In the EO file where we store all the AT information, you'll be able to have your quality report. So, as I said here, there's depending on the workflow that you will use, if you use some ground control points or if you use the intensity or the DEM reference, you'll see a bit of change in the quality report. In this case, I've used the intensity and the surface model as ground reference. So the accuracy is really defined by the reference points. So you'll have a projection error in pixels. So it will give you an estimation on how well your bundle adjustment is well tied on your intensity imagery. And then you will also have the standard deviation and the number of reference points. If you want to go much more deeper in your analysis, well, we have other text files that are reported in your step 1 report, such as all the reference points, their observation on which image they're belonging, and what is the residual on each reference point, depending on which images you're looking for. So all this information is stored here. On the other end, if you're using some ground control points, well, you will have the traditional quality report, which instead of having reference points, instead of having the reference points here, you will have one window for the ground control points that were used, and another one here that if you're using some checkpoints for accuracy assessment, well, both information will be used. It's sure that if you're using ground control point and checkpoints, well, the checkpoints will really give you a good understanding or a good overview of what is the real accuracy you'll be able to have between your LiDAR and your model, because the checkpoints are not used during the bundle adjustment. So when we're trying to match the image with your LiDAR, well, the checkpoints are only there to verify if the final adjustment that we did over your block of imagery is really fitted on your LiDAR data. Once you're confident with your aerial triangulation result, which is I think the most important part in the photogrammetric processing, you really have to make sure that if you don't have a good AT, you don't want to go in further processing, because the AT is really the main part of a photogrammetric project. So once it's done, you're satisfied with your AT, well, you'll be able to use the external, you'll be able to use your LiDAR DEM for the ortho rectification. One thing that's quite important is you could use your LiDAR DEM instead of generating your own image matching DEM, because, well, if you don't really need it, the dense image matching and it's really the most consuming time, because it really takes probably around 40% of your processing workflow generating a surface model from your processing workflow with photogrammetric data. So if you want to use your LiDAR DEM, well, you're sure that your LiDAR, your imagery is controlled over your LiDAR, so you could do directly the ortho rectification on such data. So you have a few possibilities here. The first one is you could create your own DEM with your LiDAR point cloud, or if you already had your terrain model or your surface model in a raster form, you could import your GeoTIFF inside Correlator 3D and do the ortho rectification on such data. If you want to bring an external DEM in Correlator 3D, well, you'll be able to select to add a DEM here in the aerial in the DEM section, and use this DEM for the ortho rectification. As I mentioned before, the advantage of using the LiDAR for ortho rectification is usually LiDAR is much more well suited for true ortho generation because you have much more a cleaner edge on your building, and when you try to really calculate the displacement of every pixel, such as building and everything, well, you really need to have a really sharp DSM to do some true ortho generation. I think the key of having a good true ortho is really have a really good surface model and have a good fit or a good fit between where your image was positioned when it was taken and regarding to the reference source you want to ortho rectify these images. Also, you could, if you want, you could bring your DTM, your LiDAR DTM. Let's say you are under a forest environment, and you want to map, you want to have your forest mapped on a DTM based without having all this this probably wobbly effect over the trees if you're using a surface model. Where, well, you could bring your terrain model and do the ortho rectification straight on your terrain model. As for you, as if you're not familiar with the difference between the true ortho and the classic ortho, well, the main difference here is that if you're doing an ortho on your surface model, all the leaning effect of the element on your imagery will be rectified. So the building, the cars, and everything that's over the terrain and the terrain data will be rectified. So every pixel that you will look in an orthogonal perspective. On the other hand, if you're doing an ortho rectification on your terrain data, well, it's only going to be the terrain deformation that will be corrected. So you'll still have a leaning effect for some buildings or trees or cars, depending on the acquisition parameters that you add. The leaning effect could be really less if you're flying at really high altitude, but could be really important if you're flying at a low altitude with a non-metric camera with a UAV. Well, the leaning effect could be a challenge here. So it's you really need to ask yourself what is the best suited for my needs. So during the ortho rectification process, the main goal is to select what you want to have for the ortho rectification, and you'll be able to launch the ortho rectification modules. So if you want to have a DSM base, well, you will have to select your DSM, in this case here in your project tree, and check your DSM. Also, if you have some really large imagery and you don't want too much to rectify your full imagery, well, you could crop your imagery. Sometimes this could be interesting if you're flying with a UAV at a really low altitude and the leaning effect of buildings or elements that are not rectified over a DTM ortho rectification. It could be good to crop a bit the ortho because you want to reduce this leaning effect. So you should have a better result when you're generating your mosaic. Also, the crop factor should be accordingly with the overlap that you had with your imagery. Ensure that if your overlap is borderline of photogrammetric needs, well, you won't really have a chance to crop your ortho. You really need, if you have a really high overlap, well, you'll be able to crop a much more part of your orthos and really keep the nadir part of the imagery. Also, you'll be able to select the resolution that you want to have for your final ortho. Another thing that's really that's quite interesting is if you want to colorize your LiDAR point cloud, well, it's possible in Correlator 3D. So when you bring in your point cloud, you'll be able to colorize it based on the content of your imagery. So you'll be able to have all your LiDAR point clouds, so your really dense LiDAR point cloud in a colorized form. Another thing that's quite that's another advantage is if you want to colorize your point cloud. In this case, if I load one strip that I have colorized, you'll be able to load your small section of the point cloud. In this case, so here I have my LiDAR point cloud that is colorized with my imagery. So one thing that could be useful is we see these days more cameras that have more than the regular RGB band. So some of them had an infrared band, which brings more information through your imagery. Well, when we colorize the point cloud, you'll be able to go in the point cloud colorization and then select what band you want to color your point cloud. So let's say you have 4 bands in your imagery and you want to have your point cloud colorized, let's say in a CIR way. So you want to have the green, the red, and the near infrared. You'll be able to select the corresponding band that let's say if you have 4 near infrared, you'll be able to select your near infrared band here, then the red, and then the green, and you'll have a CIR band, a CIR point cloud colorized. This gives you, depending on the analysis that you want to do, let's say in forestry, the infrared is a much more valuable information because it could help you distinguish between some trees, if the trees are healthy or not healthy, and some metrics, some color metrics could be generated from there. So you could calculate some ratio, some NDVI, and stuff like that directly from your point cloud. So this is another element that could be quite important to bring. Another thing that we could generate that you could generate from your LiDAR DEM, DSM, or DTM. Well, you could generate contours. So we have tools. If you bring in your LiDAR data and you want to generate contours from your LiDAR, well, you'll be able to generate your LiDAR your contours in a really accurate way. And then you'll be able to choose the right interval for your contours. It's sure that if you have an interval that's really close between your contours, well, you'll get really the microtopography of your terrain. However, if you get contours that are quite that have a big interval, well, you'll have something that's much more smoother. And maybe if you want to superpose it on the map, well, it could give you an understanding or perspective of the terrain relief over an area. In the software, if you want to generate your contours, so basically we have a contour extraction. So you select your surface model or your terrain model from what you want to generate your contour. Usually, you probably want to generate your contour from your terrain element. Because if you want to represent your terrain, so you select in this case your terrain model, and then you'll be able to generate contours from this terrain data. So in processes DEM contour extraction, you'll be able to select the interval, and then if you want to add an offset, also if you want to add an attribute in your shapefile that contains the elevation, and then you'll be able to generate some contours from your LiDAR elevation data. Finally, the last thing that I would like to talk about for this presentation is if you want to perform some change detection. Well, LiDAR, as I mentioned at the beginning of my presentation, LiDAR is much more expensive than photogrammetry data. However, since LiDAR can map underneath the canopy, well, it could be suited if you want to use correlator 3D to measure the height of your trees. Well, you could generate a surface model from your imagery based on your LiDAR aerial triangulation, and then use this surface model and the LiDAR DTM reference, and it will give you the difference between the DEM and your LiDAR and your top of your canopy, and it will basically give you the height of your tree, and from there you'll be able to generate other source of metrics such as biomass and basal area and other information from for a forestry perspective. There's there is you could use your reference DEM, and then if you have different data of imagery, well, use your reference DEM as your AT, and then compare the change between your photogrammetric processes. So the first thing could be, let's say, so if I want to measure the height of the change of height in my trees, so I could use the first year the imagery and the LiDAR, and then 5 years later only flown an imagery project, and then use the LiDAR DTM, which we usually assume that there's not big changes into the terrain elevation, and then generate a canopy height model from this. So you'll subtract your photogrammetry DSM from your LiDAR DTM, and then you'll be able to compare and see the changes in your vegetation growth for analysis. This is one element that could be used for the change detection. And also you could, depending on what you want, you could also show those changes in your mosaic. So if I show you in the software how it looks, if you want to perform a change analysis, well, you'll need to import your DSM and your DTM, depending on what you want, and then processes. You'll be able to perform a change detection. So you'll be able here to add the reference DEM and your reference DEM, which should be your DTM, and then your comparison should be your surface model, and then you'll be able to, if you want to display your changes on your mosaic, and you can only change from depending on what what you want. So if I want only changes from, let's say, 3 to 15 meters or 15 meters and more, this could be done depending on your needs. So this is what ends my presentation.